What's that?
Booting.
Yeah. So, OpenBTS Layer 1, the reason I'm giving this is because I know there are people hacking OpenBTS Layer 1, and people using Layer 1 pieces of OpenBTS in other projects. So maybe you'll find this useful. Layer 1 is everything between the antenna and the Layer 2 frame. So it includes modulation, the actual radio modem, and also all the forward error correction stuff, the interleaving and parity checking, and convolutional decoding. So the image there is actually, that was the first signal that we got out of OpenBTS when it got up and running. That's a classic image of a GSM beacon channel. And if you see this little lump right here, oh, you don't see my cursor. There it is. That little lump is the frequency correction burst. And this scope that we used to do this is probably older than most of the people in this room. If you look closely, you'll notice that is not a raster image, that's a vector image. This is a piece of 1973 test equipment. I'm going to start out talking about amplitude modulation. Basically, what you're going to do with amplitude modulation is you're going to take your signal, your actual information signal, which we're going to call X, starting in the upper left-hand corner, and you're going to multiply it with a sine wave carrier, and that sine wave carrier is your actual radio carrier. And if you look at that in the frequency domain on the right side of the image, capital X is a function of omega. Omega is frequency, and I've labeled the bandwidth of X is the width of X's spectrum in the frequency domain. So in the lower left part, right here, is what that modulated signal looks like in the time domain. You see drawn in red, you see the original information signal X, and then in blue you see what actually came out of the modulator is the radio carrier and its amplitudes being controlled. Now, if you look at this in the frequency domain in the lower right-hand side, what you see are two copies of the original signal, one in positive frequencies and one in negative frequencies. And these two copies are mirror images of each other. And for a real valued signal, the spectrum of X is also symmetric about the zero frequency. So one side of the spectrum is a mirror image of the other for a real valued signal. That means when you look at this image in the upper right up here, there's a two-way symmetry here. But when you go down here into this area, what you actually have going on down here is four-way symmetry. Because the original spectrum is symmetric, and now you've made symmetric copies. And so while this seems like really elementary stuff, all this stuff about spectral symmetry becomes really important in the design of the radio modem inside OpenBTS layer. So, simple example, BPSK. Basically, BPSK is you're going to do amplitude modulation driven by binary waveform. You're going to take your binary data, you're convert it to a plus minus one waveform, and you're going to run it through an amplitude modulator. And if you look in the upper right here, what you see is the spectrum of that square wave, and you see a main lobe that's at half the symbol rate. The bandwidth there, the total bandwidth actually plus and minus is a symmetric spectrum, so the total bandwidth going into negative frequencies is the symbol rate. But then you see side lobes coming out, and that's because your square wave has sharp edge transitions, and those sharp edge transitions have high frequency harmonics in them that spread out into the surrounding frequencies. And then again, you look at the resulting amplitude modulated spectrum. You have two copies of the original spectrum of the signal, and you have the same four-way symmetry. So first thing you want to deal with if you're building a radio modem is you want to get rid of all those side lobes. You're going to do that using doing something called pulse shaping. So you see red's the original square wave, and green is the pulse-shaped signal. It's basically a low-pass filter. And that low-pass filter eliminates these side lobes. And here's your resulting modulated spectrum down here. Now you always have a little bit of excess bandwidth. So, there's a little bit of a side lobe hanging off there, but not nearly with the problem that you had before. Now, when you start doing pulse shaping, and again, this seems elementary, but this all plays into the radio modem later. When you start doing pulse shaping, you have a trade-off between excess bandwidth and ISI. Filters that tend to really...
ISI is intersymbol interference.
Sorry, intersymbol interference. Intersymbol interference is when energy from one symbol bleeds into the symbols around it. Filters that have very tight frequency transitions, like this one down here, also tend to have a lot of ringing. They spread out in the time domain. They have a lot, and thinking of this as from a computer programmer's point of view, these filters have a lot of memory. So they have a lot of state information associated with them. They have a lot of memory associated with them. And that memory, the length of the memory that's associated with filters is directly related to how rapidly it transitions in the frequency domain. So you get to play a trade-off. Now, one of the most commonly used filters in digital communications today is something called a root-raised cosine filter, which is the square root of what you see right here, at least in the amplitude domain. And the reason it's taken as a square root is because normally in these systems you have one pulse shaping filter on the transmitting side, and you have an identical pulse shaping filter and a correlator on the receive side. So the total transfer function is actually going to be the convolution of those two. So anyway, the total transfer function ends up being something like this. And the root-raised cosine filter is a parameterized filter. There's a parameter beta that you can adjust to do your ISI transition, to do your intersymbol interference transition bandwidth trade-off. So with beta equals 1, we see the minimum amount of intersymbol interference, which also has the most excess bandwidth and the softest transitions. And then in the case of beta equals 0, which is the blue line, that's the most aggressive filter roll-off, but it also has the most intersymbol interference. Now, intersymbol interference is not the end of the world. There are ways to deal with it, but it complicates the design of your receiver. So for any application, it's a given trade-off between excess bandwidth, transition bandwidth, and receiver complexity, and you'll pick the appropriate parameter for your application. So how do you demodulate amplitude? How do you demod AM? Funny enough, the demodulator for amplitude modulation looks just like the modulator. You have a sine wave carrier. Your input signal here is going to be multiplied by some sine wave carrier. And what you get out is a sine squared, some sine squared function times the original information signal. And for those who remember your secondary school trigonometry, when you break this out, you see two terms in the math here. One of those terms is a copy of the original information signal. Another of those terms is the information signal modulated by another carrier at twice the original frequency. So the spectrum you see down here, you have your so-called baseband signal, which is an image of the original signal, and then you have these harmonic harmonic images, mirrors, way out at twice your carrier frequency. And what you do now is you just take a low-pass filter, select out your baseband signal, and you've recovered your signal. Bam. So in this example, we've shown a sine wave that's in phase with the original modulating signal. What happens if your demodulating carrier is not in phase with your original modulating signal? Now what? What happens is when you work out the trigonometry, the baseband image just disappeared. It's gone. The harmonic images at twice the carrier frequency are still there. The baseband's gone. And at first you think, oh, that's horrible. This really complicates things. And then you realize, no, this is a huge opportunity, because I can modulate another information signal on this quadrature carrier, and I can send two information signals using the same system. And they'll be orthogonal to each other. They'll just disappear. One will just disappear when you look at the other. This brings us to the topic of spectral symmetry. Why does that work? Why do we appear to be pulling information out of thin air when we do that? The answer is you're not pulling information out of thin air. The problem is, because you live in the real world, you don't think about imaginary signals, and they're always there. They're not really imaginary at all. So when we talked about spectral symmetry, the real valued signal, here you have a real valued signal X, and it has a symmetric spectrum about 0. Now, if you think of it, if you've ever worked with Fourier transforms in software, and if you work with FFTs in software, you'll start out, you'll take n real valued numbers, you'll stick them into an FFT and get out n complex numbers. The complex numbers have twice as many components. It took twice as much memory to represent it. Where did the information come from? There's no information there. They're symmetric. Half of them are just negatives of the other half. What the FFT really wanted was a complex valued input. You put in n complex values, you get out n complex values, you get out just as much information as you put in. And what that means in the frequency domain is the spectrum is no longer symmetric. There's no redundancy in the spectrum anymore. That your negative frequency part of the spectrum is not the same as the positive frequency. There's another special case, the Hilbert transform relationship. Hilbert transform is a trick that's used in some communication systems, where you can take the real valued X and you can synthesize an imaginary component to generate a complex X in which the negative frequency part is 0. It's just not there. And this was used for improving the spectral efficiency of analog modulation systems, analog amplitude modulation systems for years. And they call it single sideband. So here's the modulator, the general case of amplitude modulation with in phase and quadrature channels. So the in-phase channel, the in-phase and quadrature channels are multiplied by two carriers that are out of phase with each other by 90 degrees, and then you sum them back together. Here's my bad drawing of one, but it's the same device. So what you've done is you've gone from 4-way symmetry to 2-way symmetry. The signal that's coming out of here, this is a real valued signal comes out of here, because you can't have two voltages on a wire at the same time, but the properties are such that it appears that what you did was you took a complex valued signal and applied amplitude modulation to it, and you ended out with spectra that are no longer symmetric about the carrier. And all modern communication systems operate that way. So your first example of a real signal, a real communication signal, somebody actually uses QPSK. In QPSK, you're modulating two binary symbols on every symbol period. So you have an in-phase symbol stream and a quadrature symbol stream, and if you look at the in-phase and quadrature components on a two-dimensional plot, what you see are these 4 points that represent the states that the signal occupies at the middle of each symbol period, and then these other lines represent the possible transitions. So this type of plot is called a constellation plot, and it's a pretty common way to express the structure of modulation when you're working in this problem space. This is a constellation plot of a UMTS beacon, and what it is the sum of many QPSK signals. And these sums form larger and larger grids. As you shum together lots and lots of QPSK signals, they form larger and larger grids, in the I and Q space. Which is an example of a real-world case of QPSK gone mad. Differential QPSK. In differential QPSK, you're going to constrain the values of I and Q using a gray code. And you're going to say that from one symbol period to the next, you can't change both bits. You can only change one bit at a time. And what happens is when you impose that rule, the signal no longer crosses through the origin. So instead, the signal only transitions along the boundary of a square among these 4 points. You're like, why in the hell would you do that? You've built a system that's more complicated than BPSK, but it doesn't transfer any more information than BPSK. Why would you do that? The answer is something called crest factor, and this comes into play again as we keep moving down this path. Crest factor, Dieter talked about crest factor earlier with UMTS. Crest factor is the ratio between the mean power level and the peak power level that can be produced by your modulation. And by keeping signals out of the origin, by trying to constrain the signal to a circular space in this IQ space, you minimize crest factor. So a signal with crest factor of 1 would be a perfect circle, just a clean circle in this space, and we'll see some examples of that. GMSK is exactly that. The DQPSK, it has a crest factor that's not that far off of 1, because the signal is confined to this sort of annular ring that never goes through the origin. So the reason you do this, to dig a little further into why you want to avoid crest factor, it has to do with the way that power amplifiers are built in the real world. A power amplifier, a linear power amplifier is a device that draws constant power. It draws constant power. Some of that power at any given moment is being diverted into the antenna, and the rest is being converted to heat. That means that whatever the maximum peak instantaneous power is of your signal, your amplifier has to be able to generate that much power at any given moment. It doesn't matter what the average is. The power amplifier has to be able to accommodate the peak power, the peak instantaneous power that your signal can generate. Which means that your amplifier is going to be drawing that much power all the time, no matter how much power you're transmitting at any given moment. So this is why crest factor is larger than about 4, lead you to really just waste a tremendous amount of power. So if your basically your crest factor is basically the factor of power that you're going to waste in your power amp, in order to have enough headroom not to distort and clip when these high-powered peaks go through it. Because like I said, that's the best way to think of the amplifier. It's a device that's drawing constant power. It's drawing constant power, it's converting most of it to heat. And then some of it gets diverted into the antenna. And the more you can control that ratio, the better off you're going to be in terms of power consumption. So this is why you would do DQPSK. So you're not transmitting any more information than BPSK. Your modulator is twice as complicated, but you've gained a lot of efficiency in your power by doing this. Next up, frequency modulation. Typical implementation of frequency modulation in a modern system. You have some information signal X that's driving a VCO. That VCO is producing some carrier that's varying with the voltage of the input in real time. And that's being decoded by PLL, and you're recovering some copy index on the other side. And what's the spectrum associated with FM? In the general case, the spectrum associated with FM is a nasty mess. It's a bunch of Bessel functions and crazy stuff. But something to bear in mind, there's a property of FM called the modulation index. It's basically the bandwidth ratio. It's the bandwidth ratio between the bandwidth of the driving signal, your X, and the frequency excursion that you're doing in the radio domain. So simple cases you can't analyze. Frequency shift keying. Frequency shift keying is basically it's the frequency modulation analog to BPSK, and you have two carriers. You basically have two carrier frequencies, and you're switching between them depending on whether the input's a 1 or a 0. And there's a modulation index associated with this. It's the carrier spacing. It's the ratio of the carrier spacing to the bandwidth of the input signal is your modulation index. And if you look at this in the frequency domain, you see the same kind of spectral symmetry that you saw back in amplitude modulation, and that's because each of these carriers, this is the WC in the bottom is the center frequency. It's the average of the two frequencies that you're using. So this is not what you see at the bottom of the screen is just like one side of the true spectrum. There's a negative. There's another copy of all this over in the negative side. So there's actually 8-way symmetry if you take the whole spectrum into account. But over here on the positive side of the spectrum, what we see are two BPSK-like signals sitting around some center carrier. And the reason they both look BPSK-like is because each one of them is just being turned on and off pretty fast, and that's like BPSK with a DC offset. But you have these two BPSK-like spectra around some center frequency that you're not actually using. So minimum shift keying, MSK, is where you say we're going to take these two spectra, we're going to use a small modulation index. We're going to use the smallest modulation index we can, and we're going to bring these two different carriers in as close to each other as we can. And when you do that, the power, they start to sort of merge, and they stop looking like two Gaussian lumps and start looking like one Gaussian lump. So MSK is just, it's frequency shift keying, where you're using the smallest modulation index that will mathematically work without destroying your information. And that finally brings us to GMSK. So in GMSK, it's minimum shift keying, where the frequency transitions, the driver for the driving voltage of the VCO is being filtered with a Gaussian filter, so that you eliminate side lobes. And what you end out with is a spectrum with a bandwidth that is the same as your symbol rate. And that's what you end up in the frequency domain, is a spectrum with bandwidth the same as the symbol rate. What you end up with in the time domain, or on the I and Q domain, is you have a signal with constant modulus. It only moves on the unit circle, and you have 4 constellation points. And the signal moves from one constellation point to the next in 90-degree steps, and which way it steps depends on whether the input was a 1 or a 0. The one downside of this is the Gaussian band limiting of the VCO input does produce a lot of ISI, but something very, very clever happens to that later. The other thing about this GMSK signal, if you remember back to the 4-way symmetry that we talked about here, the 4-way symmetry still exists in there. So within this spectrum of the GMSK signal, there's still a kind of 4-way symmetry inside there. Even though it's not as visible anymore when you look at the spectrum, it's still there. So, here's the amazing thing about GMSK that's used in the GSM system. If you remember back to DQPSK, we had 4 constellation points in the square, and we were just transitioning among them. Now we have 4 constellation points in the circle, and we're transitioning among them. Even though DQPSK is fundamentally a form of amplitude modulation, and GMSK is fundamentally a form of frequency modulation, it turns out that they have a lot of very similar properties. Except GMSK is superior from the point of view of a power amp. GMSK is a better signal because it has an even lower crest factor. It has a crest factor of 1. So everybody's like, oh, that was about software. So what you can do, where it starts getting very clever, you take the GMSK signal, and for every symbol that you see, add another pi over 2, another 90-degree frequency step. So now what's happened is, instead of having a signal that steps plus and minus 90 degrees, it now steps either 180 degrees or doesn't move at all. Now the way you apply an ongoing frequency shift, like an ongoing phase step like that, is by frequency shifting the signal. So you're going to frequency shift the signal by 1/2 of, but actually I think it's by 1/4 of the symbol rate. When you frequency shift the signal by 1/4 of the symbol rate, what you've done is you've taken GMSK, something that was a fairly mathematically complex frequency modulation, and you've produced something that looks and acts just like BPSK, which is the simplest, stupid amplitude modulation you can do with a digital signal. The only difference is that in BPSK, the transitions, BPSK is a real valued signal, the transitions are just along the real axis. In this unrolled GMSK, the transitions are still along a unit circle. And the way that happens, you can think of it as BPSK with this complex value channel filter. So because it's a complex value channel filter, the signal can deviate from the real axis during transitions. And if you draw this channel filter out, it's a Gaussian filter, and then there's another component that's kind of like a Gaussian but 90 degrees out of phase. And that 90 degree out of phase complex component is what's causing the signal to transition off of the real axis during transition periods. But the other part of this is that when it transitions like this, if you remember back when we talked about ISI from the channel filter, nearly all the intersymbol interference that's inherent to GMSK is happening along the imaginary axis. So all you do is just throw away the imaginary component of the signal. So if you look at the receive side of the OpenBTS demodulator, what you see in the first stage demodulator, what you see is a frequency shift. We're going to frequency shift the signal by 1/2 the symbol rate, and then we're just going to throw away the imaginary component. And that's it. That's the demodulator. And I guess the reason I've taken, I don't know how much time I've taken to get through all this, 20 minutes maybe? The reason I've gone down, 25, thank you. The reason I've gone down this long explanation is because a lot of people dig into the OpenBTS layer 1 and they're looking for shit like phase lock loops and all this crazy crap you see in the specification describing how to construct these signals. And that's not at all what's happening in there. What's happening in there is we're going to frequency shift the signal and just throw away the imaginary components. It's just that simple. And when we construct the outgoing signal, we do just the opposite. We construct a BPSK signal, we apply the complex channel filter, and then we frequency shift it. So if you read what the spec says about how to build the GMSK signal, they're phase modulators and all kinds of crazy stuff in there. You don't need any of that. It's a convolution and a frequency shift. And the frequency shift by 1/2 the symbol rate mathematically is very simple. It's just alternating, on alternating samples, you just negate one of the components to get your 1/2 symbol rate frequency shift. So on every other symbol you negate the real component, on every other symbol you negate the imaginary component. So the mathematics associated with these frequency shifts, the computation associated with these frequency shifts is very simple because you're negating samples in a regular pattern. Okay, next. The other part of GSM layer 1 that people usually don't understand is convolutional encoding. This is a convolutional encoder. And what it does, it takes an input signal and runs it through a memory, a tapped delay line, a shift register. And then there are two output functions, each of which is a Galois polynomial based on the shift register content. This is an exclusive OR of a bunch of shift register states. And you have two of these that are very carefully selected, and you have an output that alternates between, you have a total output that's an interleaving, an alternation of these two polynomials. And for every input symbol, you get 2 output symbols in this particular example. So this would be called a rate 1/2 coder. You could have a rate 1/3 coder where you have 3 polynomials and every input gives you 3 output symbols. GSM uses rate 1/2 coders all over the place, except for a few cases in GPRS. So what this coder does is it introduces a very structured, mathematically optimal kind of redundancy in the output bit stream that allows you to destroy a lot of bits and still, in fact, in principle, destroy up to half of the transmitted bits and still recover the original input sequence. The problem is, how do you do that? It sounds great in principle, but how do you do it? The only way to really do it is you're going to hypothesize input streams, you're going to run them through the encoder, and you're going to compare them against what you received until you find the best match. And originally this is a problem that is exponential with the length of the input stream, but in the 60s a guy named Andrew Viterbi pointed out, no, it's not exponential with the length of the input stream, it's only exponential with the length of the delay line. It's only exponential with the size of the shift register. So here's the Viterbi algorithm. This is usually not the way it's presented in engineering text. There are 3 steps. You're going to start with a pool of candidate sequences. In the first step, you're going to branch the candidates. So for each candidate, you're going to append, for each candidate, you're going to branch into 2 new candidates, one of which is appended with the 1 and the other is appended with the 0. And these candidates are going to represent hypothetical input sequences that you're testing. You're going to generate the output and test them. So in the first step, you take each candidate, you make 2 copies, and you append a 0 and 1 or append a 1 on the other. And the number of candidates in the set is exponential with the size of the shift register. Second step is cost estimation. So in the second step, you're going to take each of the candidates, you're going to run it through the decoder. You're going to look at the corresponding decoder outputs for the candidate input. And you're going to check the cost. You're going to look at the difference between that, between the output associated with your hypothetical input and what you actually received. And these are called costs. And you're going to estimate the cost for each of your candidate sequences. You're going to estimate the cost associated with that candidate sequence. Then in the third step, you're going to take all these candidates. And for candidates that have common suffixes, you're going to choose the one with the lower cost. So you're going to go back and you're going to group the candidates together in a different pattern than when you branch them. And then within each group, you're going to take the one minimum cost. And then somewhere among all these survivor sequences, there's going to be one that has a global minimum cost, and the global minimum cost is your best fit symbol estimate. And those of you who are real mathematicians among us, maybe Sylvan, are going to say, oh, you're hand-waving around a lot of shit here. You're right, I'm hand-waving around a lot of shit, but, this is how it looks. This is how it looks, at least the way it's implemented in OpenBTS. This is not a trellis diagram. Those of you who've seen trellis diagrams before, trying to understand the Viterbi algorithm, this is not a trellis diagram because this makes sense. So starting on the right, we're going to create, this is like the very first stages of running the Viterbi decoder. Starting on the right, we're going to synthesize some candidate sequences. In this case, this is a short, constraint length 2. That is a two-point shift register, which is smaller than you would ever use in practice, but it makes the diagram fit on one page. At rate 1/2. So you're going to start by synthesizing all the possible shift register states as your first set of candidate sequences. So you're going to populate your candidate set. Initially you're going to populate your candidate set by generating all the states that the shift register could have. Brute force. Just brute force. Although in practice, normally, in practice, the protocols are usually designed in such a way that the shift registers are initialized to all 0 at the start of the decoding process. So in a real protocol, the protocol's been structured so that the only candidate you really needed to generate was this one. But if I'd only put that on the slide, it wouldn't make quite as much sense. So in the branching phase, for each of the candidates, for each of these original candidates, you're going to generate 2 new candidates. Then you're going to take these new candidates and you're going to run all of them. You're not going to run all of them through the decoder. You're going to stick all of them in the decoder and look at the outputs that come from the decoder. And then compare those outputs against the actual input signal. Do your cost calculations. And then on the basis of those cost calculations, you're going to prune the candidate set. And for candidates that have common suffixes, you're going to keep the candidate with the smallest cost. And that becomes a survivor. And you do it again. You just keep it for every symbol period, you just do this process. And as you go along, and in this case the red path will show some example of some minimum cost sequence as it evolves through this algorithm. In the case of GSM, I believe in GSM what's the order? I think it's a 5th order. No, do you remember? You don't remember? I think it's a 5th. I think the shift register for your standard GSM, there's like one Viterbi coder that's used all over the place, and I believe it's shift register length is 5. So
yeah, there is 16 states.
What's that?
There is 16 states.
Oh, shift register length is 4. Okay. Which means that there are, in any given phase of this, there are going to be 14 candidates, 14 survivors, and 32 candidates at each phase of the algorithm. This, in UMTFs, the corresponding coder is a 9th order coder, which means that at any given point in this algorithm, you're going to have 512 survivors and 1,024 candidates. And at that point, you start using what are called state reduction algorithms, and you don't actually generate the whole state space because you know the things that have certain costs are extremely unlikely to ever lead to minimum cost solutions. You just ignore them. And there are what are called state reduction algorithms, like the T algorithm or the M algorithm, that can be used to avoid having to evaluate all of the candidates. There are certain candidates that you know you don't have to bother generating to keep that trackable. SSE cost estimation. So, remember back, the reason I'm bringing this up, there was a discussion of this as it applied to encryption, decryption in OpenBTS. This question came up. How do you apply an exclusive OR to the input signal? It's not binary. What are we supposed to do? The reason the question comes up is because when we take this signal and slice it, we don't really slice it. We just quantize it. We quantize it along that axis, and we preserve that information. Because if we slice it, if we slice it, we may take a signal that was close to the origin. We may take a symbol that was close to the origin, that was somewhat indeterminate value, and artificially force it to one side or the other. And we do that, we're destroying information. So we don't destroy the information, we just quantize it. So then we get back here, what we're really doing, we're doing the cost estimates in the cost estimation phase of the Viterbi algorithm. We're not comparing bits to bits. We're comparing hypothesized output bits against an input signal which is not binary. And that means that in this case, when the signal was in some indeterminate state, we're not going to force the Viterbi algorithm to make a bad decision. You know, if the signal is in an indeterminate state near zero, the cost associated with deciding a 1 or deciding a 0 in the Viterbi algorithm is going to be about the same. If you force that signal to one side or the other by quantizing it, now you're going to cause the Viterbi algorithm to try to make a decision it really didn't have to make based on information that you just pulled out of your ass. So this is why, and this comes in OpenBTS in the implementation of encryption. What you have to do in order to make this work is you're simply going to invert the sense. You're basically going to do the equivalent, something like a sign inversion. When you apply encrypt, when you're performing the decryption phase, the deciphering phase, is you're just going to invert the sense of each of these soft symbol estimates. And the reason you have to do that in GSM is because ciphering was an afterthought. And it's added at a very low level in the stack, at the point before you've actually finished recovering the signal. So you're not going to flip bits on the decoding side. You're going to invert the sense of these soft symbol estimates. And you gain a lot by doing soft decoding. You gain about a 2 decibel improvement by doing soft decoding. And 2 decibels is, in terms of range, effect on range and performance, 2 decibels is a lot. So, here's the general structure. The general structure of the receiver for OpenBTS. We get the samples from the radio, we apply the channel filtering. And from the channel filtering, we have two correlators, one of which we're going to use. One of them is the Ratch burst correlator, which is big, and the other is mid-amp correlator. And we try not to use the Ratch burst correlator when we can avoid it, because it's actually the most computationally demanding part of the entire system. And we're going to apply our Laurent demodulation, where we do the phase unwrapping. We do a phase unwrapping and we strip off the imaginary part of the signal. We get something that looks like BPSK. And once we have BPSK, we can run that through a decision feedback equalizer. And we want to have to talk much about the structure of the decision feedback equalizer, but it's for multipath negation. And then that's the radio burst gets sent to the layer 1 after forward error correction. On the transmit side, the transmit side of OpenBTS does two things that catch people by surprise when they start looking at the code. One of them is that all the channels that are running in OpenBTS and generating outputs are asynchronous. They can generate outputs for different timestamps at different. They can generate outputs at different times. They're supposed to be transmitted at different times. And because of that, we feed them all into a priority queue sorted by timestamp. And at the head of the priority queue, there's a little loop that's driven by a clock. And it looks at the head of the priority queue. And if there's something that's ready to be transmitted, we put a copy of it in a table called the filler table, and then we transmit it. If there's nothing ready to be transmitted, we go to the filler table and we take a copy of something that was transmitted recently and we transmit that instead. The other thing we do is we flush the priority queue. Things that are in the priority queue that are too late to be transmitted get flushed out. So you occasionally see these stale burst warnings in the log, and that's what that is. It's the process that's pulling shit out of that priority queue, realizing that there's no possible way that this can be transmitted at the requested time. It came too late, so we throw them away. Well, we don't just throw them away. We make a copy in the filler table, then we throw them away. But the purpose of the filler table is that in GSM, in any of these digital radio systems, you have to transmit something, even if it's just silence, even if it's just zeros. You have to send something to the digital analog converter. You can't have a discontinuous data stream going into these D-to-A converters, or you start running into all kinds of synchronization problems. You have to transmit something. So the way the filler table is structured, for any given physical channel in the GSM system, any given time slot, there's some modulus associated with that time slot. There's some multi-frame size that's associated with that time slot. And the length of the filler table for any given time slot is matched to that multi-frame size. So there are actually commands in the control interface for OpenBTS with the transceiver where you tell the transceiver what multi-frame size you're transmitting on a given slot. The reason you're telling it that is so that it can configure the filler table. So then, when we transmit something, we put a copy of it in the filler table. We put it at the frame number position modulo the multi-frame size in the filler table for that slot. And then if we need to transmit something and we don't have anything available coming out of the queue, we go to the corresponding frame position modulo the multi-frame size in the filler table and get something to transmit. If you look in OpenBTS, if you look up in layer 2 and higher up in layer 1, you can see where we exploit this in different places. For example, in layer 2, LapDM, you're constantly supposed to be generating an idle pattern. Idle channels have to generate an idle pattern. Like on an SDCCH, you can't have dead air on an SDCCH. There has to be an idle pattern. Well, the way we generate the idle pattern in OpenBTS is we send one copy of the idle frame. Actually, we send enough copies of the idle frame to fill the table. That's what we do when we know a channel is about to go idle for some period of time. That's the last thing we do. And then we don't have to transmit anything else. The layer 2 code in OpenBTS just goes to sleep. It sends enough idle frames to fill the table and it goes to sleep. Because we know that down in the modulator is going to keep playing that same pattern over and over and over from the filler table until we change it. We do the same thing with dummy burst on the C0 carrier. The C0 carrier is supposed to be constantly transmitting. If you don't have an active channel, we expect to find something called a dummy burst, and you send the dummy burst. So the last thing that happens when when we deactivate a physical channel in OpenBTS, the last thing we do before we deactivate the physical channel in OpenBTS is we send one multi-frame worth of dummy burst, and then the channel just goes to sleep. Because again, we know that down in the modem, the filler table is going to keep playing that pattern of dummy bursts over and over and over. We don't have to deal with it anymore. Now, if we were really clever and really concerned about computational efficiency, we would make the filler table big enough to carry an entire cycle of system information messages. And then our beacon channel generator wouldn't have to send system information messages either. All we'd have to send anymore is just the sync channel, just to keep the frame numbers rolling. But these are the two things that often catch people by surprise when they're looking at that. One is the necessity of the filler table and the way we use it. And the other is the fact that the channels in OpenBTS are all running, the channel generators are all running asynchronously. So everything is done with timestamps. There's no scheduling, there's no real-time anything. We're just generating everything asynchronously in time, but time-stamping them as to when they go onto the radio channel. So this is the interface. So OpenBTS is split into two parts. The part we call OpenBTS is the forward error correction and everything above that. It's the forward error correction part of layer 1 and then everything above that. Then everything below forward error correction in the radio modem is implemented in a different binary called the transceiver. And we split it this way so that if people wanted to write completely different transceivers for radios with completely different characteristics, they could do that as long as they stuck to the interface. So in the sort of generalized case of this interface, what we have, each of these arrows, each of these streams represents a UDP socket, a pair of UDP sockets in the two applications. Yeah, we use a lot of UDP sockets. The first one on the far left is the clock. The clock in OpenBTS comes from the digital analog converter in the digital radio. That's where the clock comes from. That is the source of the clock. And from that clock, we calculate a frame number. And we periodically send the frame number across the UDP interface in a message called a clock indication message. And there's a thread inside OpenBTS that receives the clock information message. And when it receives the clock information message, what it does is it makes a note of the current real-time clock value, the system's current real-time clock value, and just stores somewhere, in some global information these two values, that this particular frame number corresponded to this particular value of the real-time clock. And then if OpenBTS needs to calculate what the current frame number is in the radio modem, it calculates it from the real-time clock of the system using that information. And that gets updated every few seconds. And it doesn't need to be any more complicated than that. Even if the two clocks are drifting with respect to each other, which they always will be, as long as you update that every few seconds, you'll be fine. The rest of the interface is pairs of UDP sockets for each ARFIN. So the public release of OpenBTS is single ARFIN. The commercial release has been multi-ARFIN for quite a while now. I know Thomas Su is working on multi-ARFIN. In the commercial multi-ARFIN release, we have a pair of UDP sockets for every ARFIN. And one of them is a control channel that's used for tuning. It's used for tuning and power control and noise measurement. And the other is raw data. And when I say raw data, what I actually mean are every transfer on this UDP interface is one GSM radio burst. So on the transmit side, what you have on the data interfaces are UDP packets that contain channel bits that are supposed to be transmitted, a timestamp telling when it's supposed to be transmitted, and some information about at what power level it's supposed to be transmitted. And even though we don't use the power level much, it's put in there in case you want to support things like discontinuous transmission in the future. So if you need to send a zero power burst, or if you want to do active downlink power control on carriers other than C0, the protocol will support that when you're ready to do it. On the receive side, the downlink going from the transceiver up to OpenBTS, each UDP packet contains a timestamp of when the signal was received. It contains an estimate of the power level at which the signal was received, and then it contains the normalized soft signal pattern, normalized to an 8-bit scale. So if you want to know the actual absolute power level, you can look at the header information and know what the power level really was. But what's transmitted in the burst is normalized. That's the interface. It's not that complicated. There's a README file in the source code that, for whatever version you have, that describes how it works. That's it in terms of slides. We have a few minutes left for questions. If there are questions. Yeah.
There are two things. First, you mentioned that the array detection was very time consuming. And I was wondering, because I see that you do validate you do some analysis of the RF power to see if there was indeed a spike of power, but you do it after doing the correlation.
Yeah.
And I did some tests on receiving array CH, and I found that doing just analyzing the power of the channel before doing the correlation with a very low threshold, so that you do get a lot of false positive, but at least you can save some computational power. Not trying to correlate noise that power that's not there.
Yeah, I've had this argument with Carbon a few times.
Oh, okay.
It's his claim that the cost of doing the power estimate
Yes.
is the cost of doing the pre-correlation power estimate is it's high enough that the power, the computation that you save by not doing those extra ratchet things, it's a wash. It ends up being about the same either way. It's simpler just to run the correlator full bore. That's what he claims. I'll say that when we talk about the transceiver part, I did not write the transceiver. The transceiver was written by my business partner Harvin Samra, who's one of the other original developers of OpenBTS. But we have this discussion every 4 months.
Okay.
Because I don't always buy it either. I profiled this code, I know what it does, and that's no, don't bother, it's a waste of time, I tried it. Okay.
And the other is when you showed the pulse shape, it had a complex component.
Yeah.
But I don't see the complex component in the code, I just see a real pulse shape. The generate pulse function?
Yeah.
Is that the pulse that you showed in your slides?
Yeah, but I believe the complex part, is generated from the real part. The complex part is actually the derivative of the real part, if I remember correctly. Well, maybe there's something going on there I didn't know.
Okay, I'll recheck to make sure.
Yeah, that thing.
Yeah, exactly.
So I'm pretty sure the complex parts, the imaginary part is generated from the derivative of the real part. But the fact that you don't see it in an array somewhere in the code, you don't need it on the receive side.
Yes, but the same GSM pulse is used for modulation.
Right, you're right. So why don't you see it on the transmit side? That's a good question.
Maybe I just missed it.
I don't have a good answer for you. Why do you not find it? I don't have a good answer for you.
Because it's imaginary.
Right.
It's obvious, isn't it?
It's obvious. It's imaginary. Yeah.
Between the lines.
Let's see some.
Ja, über der Kreide ist es vielleicht nicht so lustig.
Kann man besser streichen. Fingerzeiten, okay.
Let's see. I'll look into that and see if I can't give you an answer, because that's disturbing me at the moment too.
I mean, at some point you're gonna get a complex component for your signal because you still do the rotation after converting with the pulse. But
Yeah, we still do the rotation, but what's going to happen is you'll violate the constant modulus. You'll get all kinds of overshoot and looping. If you were to look at the result in the IQ domain, what you'll see is a little looping around the constellation points. It doesn't hit them, it overshoots them and loops back. It'll be a spectrum that'll look a lot more like a messy QPSK.
Yeah, when you plot the constellation at that point, it's not really a point. It's more like a zone around the.
Yeah.
Do you have any insight on how the DFE works? The equalizing?
There, I can't don't have a lot of good insight on the DFE. So, but certainly if there are questions about, I mean, I can tell you some changes that had to happen. Certainly in order to support handover, those discussion we had, the other day, where, bands had to be added to the control interface to tell the radio modem to look for an access burst on a particular slot where it normally would not look for one. So the access burst detector that's used there, it's the same access burst detector that's used for random access bursts, it's just applied in a different place. But again, because of the computational demand, we don't do it all the time. We don't run them in parallel, we switch it on, you know, when we know to look, when we know an access burst is probably going to come, we turn it on. And once we've received and verified an access burst, we turn it off.
So that's done the same way in other BTSs.
That makes a lot of sense.
In fact, even on the RATCH, it may need to be explicitly turned on. I mean,
After
because still, to make the interface more orthogonal.
Yeah.
When you want RATCH detection, you just have to turn it on wherever that might be.
Yeah. There were other changes. The filler table mechanism that we have implemented does not. The way the filler table mechanisms implemented in pre-GPRS systems doesn't work for GPRS. The filling rules, the idle filling rules for GPRS are different than for LAPDM. And so the idle filling mechanism that we used in the pre-GPRS systems doesn't work. So that had to change.
And the priority queue, do you know, or is it bounded in size? I mean, how far in advance can OpenBTS send the burst?
There's no limitation, because there really isn't. So what we have to do is there's no limitation because most of the, because UDP is, you know, there's no blocking when you write to a UDP channel. So to be real clear on that, people who don't know the code that well. Like that, okay. So you see this thing with asynchronous channels. So here you see these asynchronous channels feeding the priority queue. This priority queue is in the transceiver, it's not in OpenBTS. It's on the transceiver side of the UDP interface. Of course, there's no blocking on UDP, so what you do for channels, for what we call, if you look in the code, some channels are referred to as generator channels. And generators are channels that aren't driven, they're not driven by transactions inside the system, they're just generating fixed patterns over and over and over again. So generator channels actually have to be throttled back. So they're in the loop for every generator channel, you look at the clock to decide whether it's okay to send. And then if you're too far ahead of real time, you just sleep. But there's no mechanism inside the priority queue. You can send stuff way ahead of time if you wanted, and it just sit there for a while.
No, I was just wondering if you split it physically, the OpenBTS process and the transceiver, and the transceiver hardware and some kind of memory limitation, exactly what you need to store.
Oh. Well, yeah, usually these things don't run more than about half a second ahead. I mean, they don't run more than about half a second ahead of real time. So you shouldn't need to store more than about a second's worth of data.
At some point, the kernel will drop packets.
Well, no, we're pulling them out of the ADP sockets. They're not
stored
loaded
inside, not in the socket buffer, but in the priority queue. So.
But if they can't be pulled out,
Yes.
Well, yeah, we can eventually, yeah, if we stop.
if you stop or if there's too much coming or whatever, then they will just fall on the floor.
No, there's throttling up in OpenBTS to prevent things from running too far ahead of real time. On transaction-driven channels, that's not so much a problem because we implement blocking writes. Writes into layer 1 are blocking. The write doesn't return until the burst has been sent across the UDP interface to the radio. So they tend not to run ahead of real time because they don't know what to do. But yeah, some channels have to be throttled back. So that's it. See now it's time for the next session.
If you want to stop the recording?
No, don't give them back to me. Keep it.
Now there's another connection.